Okay, so first of all, what is a capacitor? A capacitor at its most basic is just two conductors with a small gap between such that they can store charge and thus energy between them. So the simplest case is what's called a parallel plate conductor, where we just have two flat plates of conductor, or parallel plate capacitor, where there's just two conductors parallel to each other. And capacitors will always have opposite charge on each plate, the exact same magnitude of charge, but opposite in sign. So today we're going to work through all of the quantities, all of the measurements of a parallel plate capacitor, although this process will work the same way for any other type of capacitor you might come across. So to start off with, we need to draw our charge distribution. So since they are opposite charges, we'll find that they will gather on the inside face of the conductors, trying to get as close as possible to the opposite charges on the other side of the gap. And then from that we can sketch a basic E field like so. Now we would like to find the specific value of the E field in this gap. And to do so, we're going to have to label a few values here. We'll call this gap D, and then this surface area of the plate to be A. And then we'll also have to figure out the surface charge density of these plates. That we'll denote by sigma. It's kind of a sad sigma, which is going to be equal to the total charge Q divided by the area A. So now we have all the quantities we need. We just set up Gauss's law with a cylindrical surface. You can use any type of prism-like shape, but I prefer to just use a cylinder. So we'll call that S, and we'll denote the area of each of the top and bottom caps by A. So that's just the area of the circle on top or bottom. So now let's write out Gauss's law. Q enclosed over epsilon naught is equal to the integral of E dot dA. So starting with the left side of this integral, or left side of the Gauss's law, what is Q enclosed? It's simply the surface charge density times the area. So that's little a times sigma over epsilon naught. And then what about the right side? Well, we can actually eliminate a couple of the sides of this surface. So first of all, the top side here is inside of the conductor, and we know inside of a conductor E field must be 0, since otherwise that would violate electrostatic conditions, since charges would start moving around according to that E field. So there's going to be no electric flux through that top face. And then we can also eliminate the side faces, because if we assume the plates to be infinite planes of charge, which we can safely assume so long as the plates are quite large compared to their separation, if we assume that, then by symmetry there can be no E field pointing laterally. That means that there's no E field going left, right, or into the page or out of the page. So that means there will be no electric flux through the sides of the cylinder. So then we're just left with this bottom face, which will have area little a. So this integral will reduce to E times little a, since, of course, E field is going to be the same at every point on that bottom face, again by symmetry. So then these cancel out quite nicely, and I find that the E field is simply sigma over epsilon naught, or you could write that as Q over A epsilon naught, either way. So now that we have our E field, one important thing to note about this formula that we've just derived is that it's constant. It does not change with your position in the gap between the two plates. So in other words, the E field between the two plates of a parallel plate capacitor is uniform. It's the same strength and magnitude and direction at every point. So now, from this, we can actually figure out the voltage between these two plates. As delta V, you might call it. So we know V is equal to the integral of E dr. So we simply plug in our E. We find that is Q over A epsilon naught dr And for R, we'll just go from 0 to D, so we're going across the gap from one side to the other. And then all that stuff just comes out as a constant, so we end up with QD over A epsilon naught if you actually integrate that. Perfect. So now we have the electric field and the voltage of our capacitor. Now we have a new quantity called capacitance, denoted by C, which is defined as charge over voltage. So using what we already have, we can quite easily find this. Charge is just Q. Our voltage is QD over A epsilon naught. So we'll cancel those out, kind of fix our wonky fraction here, and we find A epsilon naught over D is our capacitance. Now, one last quantity that can be useful to find is the amount of potential energy, U sub C, stored within this capacitor. So this requires a bit of a mental exercise. So to find this potential energy, we're going to imagine how much work the electric force will do if we were to let the charges across the gap one by one. So we're going to write this first off as an integral of little bits of potential energy. So we're going to look at how much potential energy is expended per little bit of charge that we let across the gap. So du, so V is defined as potential energy divided by charge, so U is of course V times charge. So then du, we'll find, is the voltage that each little charge sees on the other plate times that little bit of charge itself. So what is that voltage? Well, we have our formula for voltage right here, but that's assuming that the entire charge difference is present between the two plates. And as we let little bits of charge across the gap, that's gradually going to become untrue. Because with every little bit of charge we let across, it's going to cancel out the opposite charge on the other side, and suddenly the charge on each plate is going to be a little bit less, all the way down until there's actually zero net charge on each plate when we're done. So we'll express the initial charge with big Q, and the amount of charge we've already let across with little q, and then we can find the voltage that the next little chunk of charge will face to be this expression here. And then we just multiply by that little chunk of charge dq. So then this integral becomes this here, dq minus little q, d over a epsilon naught dq. So then we'll insert our bounds of integration. So we're going to let all of the charge across the gap in our little hypothetical experiment. So we'll go from 0 to big Q. And then we can kind of fix up our integral a little bit. A epsilon naught times d minus qd over a epsilon naught all dq. So this is going to work out to what? Q squared d over a epsilon naught minus q squared d over 2a epsilon naught. So then, of course, those are just going to simplify down into q squared d over 2a epsilon naught. So that is your energy stored in the capacitor, which can also be expressed as, let's see, what is this? So if we take out the voltage QD over A epsilon naught, let's take it out twice. So we'll find that this is actually equal to 1/2 CV squared. And you can find a couple of other forms for this that might be useful. But the point is, this is how you actually derive the potential energy stored in that capacitor.